Hello everybody, welcome back to another video. Today we're going to start off a little bit onto the journey in CT and we're going to cover the Hounsfield units today, which may seem like a minor thing in CT, but in reality it is very important. Now Hounsfield units are a universal number in CT, used to denote the attenuation of materials or structures. As a physics refresher, attenuation in X-ray refers to two processes, the photoelectric effect and the Compton scattering. In the photoelectric effect, the X-ray photon's energy is completely deposited in an inner K-shell electron. As the K-shell electron ejects, a characteristic radiation of set energy is ejected due to an outer shell electron falling back into place. Now this process is proportional to the cube of the atomic number and inversely proportional to the cube of the photon energy. This means at lower energies, which is usually those below 30 keVs, photoelectric effect is most prominent. The flip side of this is the Compton scattering, where the photon energy is partially deposited in an outer shell electron, ejecting that electron and scattering the photon. This process is directly proportional to the atomic number, or Z here, and inversely proportional to energy. Compton scattering is usually the primary process that happens in energies above 30 keV or within our radiographic range. Now in CT, due to the many attenuations that happen at multiple angles, the image is separated into a grid of voxels. As you can see from this diagram here, one region of the voxel or material represents the average attenuation coefficient of that voxel, which is denoted as mu. These separate attenuation values along one projection is called a ray sum. The ray sums are ultimately what forms the attenuation values of the whole dataset. Now, there's a funky process that happens and a sinogram is basically formed with the ray sums. This is then processed using a filtered back projection or iterative reconstruction, which helps to sharpen the image and avoid a kind of characteristic star streak artifact from just a normal back projection. Now back projection just simply means layering all the beam information kind of one over another, like a pancake over top of each other, which will form an image, but you will have that remnant streaking. Now the displayed data is characterized using Hounsfield units. This equation here represents how the attenuation coefficient of a material is converted to Hounsfield units. I'd like you all to just take note of one thing, and that is it is subtracted or compared to as a percentage of water. This is important because it explains why most CT quality assurance phantoms have water in them. This ensures scanner's uniformity, denoting the evenness of the displayed Hounsfield unit in the phantom, and scanner linearity, or how close the measured Hounsfield unit is to actually water. Right, I know there's a lot of resources online to give a scale of Hounsfield units, but I just felt like testing my Microsoft Paint skills. So here are the main values. As always, air and water are -1000 and 0 respectively. But the ones to take note here are the values of unclotted and clotted blood. Unclotted blood sits around 40 Hounsfield units, which is close to the density of grey and white matter. However, clotted blood is more dense, around 100 Hounsfield units. This is due to the high concentration of hemoglobin and expulsion of plasma. Now Radiopaedia sums up a very wonderful diagram of the density of a developing bleed, and I'll link it in the description below. So why is it important to get to know these numbers? Now there are great implications to use this core concept in everyday practice, and here are 4 examples. One, and the main one most of us radiographers can use, is to differentiate between blood and ascites in trauma presentations. Usually if fluid is present, a region of interest can be placed around the area to help suggest its composition. If it sits around 0 Hounsfield units, then it can either be ascites or just a very old bleed or a blood product. If it is between 30 to 45, it is most likely suggestive of a hematoma or acute hemorrhage. Now this can assist with determining whether extra phases, such as an angiogram or a delayed, could be useful to determine whether the hematoma is from an active arterial bleed or from a venous injury, which will be much slower. The second example we have here is related to adrenal pathology. Now patients may present for CT adrenals due to unexplained hypertension, as they produce aldosterone, which helps regulate blood pressure. Tumors located on the adrenal glands may cause overactive release of these hormones. Now again, Radiopedia provides an excellent explanation of adrenal lesions, but the most important thing for this talk is the Hounsfield units on the non-contrast scan. If a region of interest is placed over the adrenal lesion, and let's just say it's less than 10 Hounsfield units, it is most likely a benign, fat-rich adrenal adenoma, which does not require additional phases. However, if it is more than 10 Hounsfield units, a port of Venus and a delayed phase will need to be performed to define the lesion's enhancement pattern. The third example is to define lesions on the kidney or the liver. It may be useful to put a region of interest within lesions to see whether it's more likely of a cyst, which would be close to 0 Hounsfield units, or more sinister pathology, if it is more than 20 Hounsfield units. Of course, this isn't as simply just looking at density, and there are classifications such as the Bosniak renal cyst classification to help determine the nature of kidney lesions. But it still may be useful for radiographers to inform a radiologist if you see a hyperdense lesion on a non-con abdomen scan, and see contrast is needed to determine whether it is benign or malignant. Now the last example I have here is to define what we call a sentinel clot sign. Just like what I kind of showed before between the clotted blood measuring around 100 Hounsfield units and unclotted blood being about 40, this is useful for patients with acute hemorrhages, as it is an indicator of the origin of the bleed. In this case, you can see here, there is fluid surrounding the kind of inferior tip of the liver. I know I don't have a scrollable scan, you just have to trust me here. However, you might notice there is a hyperdense section of the fluid which represents the clotted blood near the site of injury. In this case, the injury came from the mesentery. Now this can be useful for patients going for interventional radiology. However, for the most part, patients may already have an angiographic and a delayed phase to assist with identifying the origin of the bleed. And that's all I have today for the Hounsfield units. I hope I've helped show the importance of knowing these values in practice. I think radiographers can use these in practice to not only assist in determining the best contrast phases for patients, but can assist radiologists in identifying any detrimental pathology. Thanks for listening, and have a good day, everyone.